The reality check: why interstellar travel may forever remain a dream. The allure of space. In recent years, space exploration has surged back into public consciousness. Visionaries like Elon Musk promise missions to Mars. NASA aims to return to the moon, and popular culture teems with images of lunar colonies, Martian bases, and even interstellar voyages. The narrative is intoxicating. Humanity, reaching for the stars, planting its flag on distant worlds. Yet, beneath the optimism lies a sobering reality, one rarely discussed in mainstream media. The path to the stars is fraught with nearly insurmountable obstacles, rooted in the unforgiving laws of physics, the limitations of current technology, and the biological constraints of the human body. Gravity, the first barrier. Before dreaming of distant planets, we must first overcome Earth's gravitia, formidable, invisible force that anchors us to our planet. As astrophysicist Yael Nazay aptly describes, we live at the bottom of an energy well carved by Earth's mass. Escaping this gravitational grip is a titanic struggle. Consider the Apollo missions. Their Saturn V rockets stood 100 meters tall, weighed 3,000 tons at launch, and were filled mostly with fuel. Millions of liters of propellant were consumed in minutes just to reach low Earth orbit, traveling at about 28,000 kilometers per hectare, mere step into the cosmic neighborhood. To reach the moon, located 384,000 kilometers away, spacecraft must achieve even greater velocities, around 40,000 kilometers per h. The Apollo program was a colossal technological and financial feat, costing billions and requiring years of research, with each journey taking several days. Even Mars, our next closest neighbor, presents daunting challenges. The average distance to Mars is about 225 million kilometers, varying widely depending on planetary positions. Launch windows occur only every 2 years, and the trip takes 6 to 9 months, exposing astronauts to cosmic radiation and the debilitating effects of microgravity. The scale of the solar system and beyond. Mars is still within our cosmic backyard. The true scale of the solar system becomes apparent when considering the Voyager probes launched in the 1970s. These spacecraft took decades to reach the outer edges of the Sun's influence, the heliopause, and are only now beginning their journey into interstellar space. But interstellar travel is a leap to an entirely different scale. The nearest star system, Proxima Centauri, is about 4.24 light-years away. A light-year, the distance light, travels in 1 year, approximately 9.46 trillion kilometers. Thus, Proxima Centauri lies nearly 40 trillion kilometers from Earth. To visualize, if the Sun were an orange in Paris, Proxima Centauri would be another orange in San Francisco, separated by a vast, cold, nearly empty void.
The tyranny of propulsion. With current technology, even our fastest spacecraft are painfully slow. The Parker Solar Probe, which reached speeds over 600,000 kilometers per hour, would take about 6,700 years to reach Proxima Centauri. More typical probes, like New Horizons, would require 78,000 years. The fundamental problem is propulsion. The Tsiolkovsky rocket equation dictates that increasing a rocket's speed, delta V, requires exponentially more fuel. As more fuel is added, the rocket becomes heavier, demanding yet more fuel, a vicious cycle with diminishing returns. Chemical propulsion, which took us to the Moon and Mars, quickly hits a wall. To reach even a small fraction of light speed would require fuel masses greater than the observable universe itself. Alternative propulsion methods have been proposed, each with its own formidable challenges. Nuclear thermal propulsion, more efficient than chemical rockets, but still insufficient for interstellar travel. Project Orion, proposed using nuclear explosions for thrust, powerful, but fraught with radiation hazards and legal barriers. Nuclear fusion, theoretically could achieve 10 to 15% light speed, but controlled fusion remains elusive on Earth, let alone in a spacecraft. Ion and plasma engines, highly efficient but produce minuscule thrust, accelerating a large ship would take centuries. Solar or laser sails, could propel tiny probes to nearby stars in decades, but scaling up to crewed ships is a monumental engineering challenge, especially with deceleration at the destination. Bussard ramjet would collect interstellar hydrogen for fusion, but the density of hydrogen in space is so low that the required collector would need to be thousands of kilometers wide, creating drag that negates its benefits. Antimatter propulsion offers the highest theoretical energy yield, but antimatter is prohibitively expensive and difficult to produce and store safely. Just a few grams would cost trillions and could annihilate the ship if containment fails. The physical and biological walls. Even if we could build a feasible interstellar craft, we would still face the ultimate speed limit, the speed of light. According to Einstein's theory of relativity, nothing with mass can reach or exceed this limit. Even approaching 10% of light speed would require unimaginable amounts of energy, and decelerating at the destination would double the challenge. Traveling at such speeds introduces new dangers. The interstellar medium, though nearly empty, contains dust grains and atoms. Colliding with even a tiny particle at a significant fraction of light speed would release energy equivalent to tons of TNT, threatening to obliterate the spacecraft. Shielding against such impacts would require technology and materials far beyond our current capabilities. Generation ships, the social and biological challenges. Suppose, against all odds, we manage to develop a propulsion system capable of reaching another star, even if the journey takes centuries or millennia. The only viable solution would be a generation ship, a self-sustaining, closed ecosystem supporting hundreds or thousands of people for many generations. This concept, a staple of science fiction, presents profound challenges. Life support. The ship would need a perfect closed-loop system, recycling air, water, food, and waste for centuries without external resupply. Even on Earth, such systems are difficult to maintain at small scales. Social and psychological stability. Maintaining a stable, motivated society in a confined, stressful environment for generations is unprecedented. Issues of governance, knowledge transmission, and mission purpose become acute when future generations may have no emotional connection to Earth. Health and biology. Human bodies are ill-suited to space. Cosmic radiation, without Earth's protective atmosphere and magnetic field, increases cancer and neurological risks. Microgravity causes muscle and bone loss, cardiovascular problems, and immune suppression. Artificial gravity systems like rotating habitats would be necessary but add immense complexity. Reproduction. The effects of space on human reproduction are largely unknown. Early animal studies are not encouraging, with concerns about fertility, embryonic development, and the health of newborns in microgravity and high radiation environments. The final barrier, physics and perspective. Even if we solve the engineering, biological, and social problems, the laws of physics remain immutable. The speed of light is an absolute limit. Accelerating a ship to even a fraction of this speed requires colossal energy, and the dangers of high-speed collisions with interstellar particles are existential. Navigating at such speeds is also a challenge. Relativistic effects would distort the view ahead, complicating course corrections and target acquisition. Conclusion. A sobering reality. The dream of interstellar travel is one of humanity's most profound aspirations. Yet, when confronted with the harsh realities of physics, engineering, and biology, the scale of the challenge becomes clear. Escaping Earth's gravity is itself a monumental feat. Reaching the Moon or Mars is an epic journey. Venturing beyond the solar system to even the nearest star is a task that dwarfs all previous human endeavors. The obstacles are not just technical or financial, they are fundamental, rooted in the very structure of the universe. While scientific and technological progress may one day bring us closer to the stars, for now, interstellar travel remains a distant dream, more at home in the realm of science fiction than imminent reality. Understanding these barriers does not diminish our sense of wonder. Rather, it invites us to appreciate the extraordinary achievements already made and the vastness of the challenges that lie ahead.